In this lecture video, we'll see how to use the CALIS procedure in SAS to fit a path model. You'll recall that path models are a special case of structural equation models, and so we can use SEM software to fit path models. We'll do this in the context of an example. So here's an outline of what we'll be looking at in this video. We'll first describe the example. We'll then review the steps involved in specifying a structural equation model, and then we'll provide a specification of the path model. We do this before we even open up the software, because there are the same steps involved in specifying the model to that software. And finally, we'll fit the path model using the LINEQS programming language in SAS PROC CALIS. So let's jump in. So we'll first provide a description of the example. An observational study was done to investigate the effects of several variables measured in the last year of high school on the academic performance of university freshmen. The manifest variables obtained in the study are as follows: the GPA in required courses during the freshman year, the GPA in elective courses during the freshman year, a high school general knowledge score, an intelligence score obtained in the last year of high school, and an educational motivation score also obtained in the last year of high school. Now, no latent constructs are being considered in this study. The goal is to model the two GPA manifest variables as functions of the other three manifest variables in order to predict the two GPA variables. There are two response variables and three predictor variables, and so a multivariate approach is needed in order to model the responses simultaneously. In addition, the predictors are not assumed to be measured without error, so the model to be used will need to allow for error in the measured values of these predictor variables. Since there are no latent constructs to be included as part of the model, a path model will be appropriate for modeling the data from this experiment and answering the research questions of the researcher. Finally, since path models are a special case of structural equation models, SEM software can be used to fit this path model. The 5 variables were measured on 150 students. Each variable was measured on each student, so there was no missing data. Each variable in the dataset was centered at 0, but the variables were not scale. Hence, each variable exhibits its original observed variation. Summary statistics consisting of the sample variances of the variables and the covariances between each pair of variables were calculated, and hence the sample covariance matrix is available for use in fitting the model. The sample covariance matrix is shown on the next slide. And so here is the sample covariance matrix, denoted by cap S. It's a 5x5 matrix, and it contains the variances and covariances of the 5 manifest variables. Next, let's review the steps involved in specifying a structural equation model. Step 1 is to identify all latent constructs or factors and manifest variables comprising the model. Step 2, specify an equation for each one-way, explanatory, predictive relationship in the SEM. Step 3, specify notation and/or values for the variances of all random variables in the system, as well as for all covariances of pairs of random variables. Step 4, identify and count the number of model parameters that need to be estimated. Step 5, construct a path diagram for the SEM. And then finally, step 6, we're going to fit the SEM in SAS. So step 1, identify all latent constructs and manifest variables comprising the SEM. Now, as stated previously, there are no latent constructs being considered for this model. Here are the manifest variables. V1 represents the GPA in the required courses during the freshman year of college. V2 is the GPA in elective courses during the freshman year of college. V3 represents a high school general knowledge score. V4 represents the intelligence score obtained in the last year of high school. And V5 represents the educational motivation score also obtained in the last year of high school. Stated in terms of this notation, the goal of the analysis is to model the two GPA manifest variables, V1 and V2, as functions of the other three manifest variables, V3, V4, and V5, in order to predict the response variables V1 and V2 from the values of the predictors V3, V4, and V5. All right, step 2 in specifying the model. We specify an equation for each one-way, explanatory, predictive relationship in the SEM. And so here are the two equations that comprise this path model. V1 is equal to lambda 1,3 times V3 plus lambda 1,4 times V4 plus lambda 1,5 times V5 plus an error term E1. V2 is equal to lambda 2,3 times V3 plus lambda 2,4 times V4 plus lambda 2,5 times V5 plus its own error term E2. Now, because the variables, and in particular the response variables, have been centered, we don't have any kind of an intercept in either of these models. Step 3, we specify notation and/or values for the variances of all random variables in the system, as well as for all covariances of pairs of random variables in the system. The variance of the error terms will just be denoted here by var of e sub I, where I is 1 and 2. The variances of the explanatory variables, V3, V4, and V5, will be represented var of v sub I, where I goes from 3 to 5. The notation for the covariances is as follows. The covariance between the two error terms, E1 and E2, will be denoted by theta sub 1, 2. The covariance of V3 and V4 will be denoted theta sub 3, 4. The covariance of V3 and V5 will be denoted by theta 3, 5. And the covariance of V4 and V5 will be denoted theta sub 4, 5. Now, the covariances between each error term and each explanatory variable is assumed to be 0. And so the covariance of E sub I and V sub j, where I goes from 1 to 2 and j goes from 3 to 5, those covariances are all assumed to be 0. And so that assumption will be imposed on the model. Step 4 is to identify and count the number of model parameters that need to be estimated. And so in the regression type of equations comprising the SEM, we see that we have 6 slope coefficients that we're going to have to estimate. We have some error term variances to estimate, the variance of E1 and the variance of E2. We also have explanatory variable variances, variance of V3, the variance of V4, and the variance of V5. We'll need to estimate the covariance between E1 and E2, and we'll also need to estimate the covariances between each pair of explanatory variables. Finally, the covariances between each error term and each explanatory variable are all set to 0, and so we don't have to estimate those. And so counting the number of parameters that need to be estimated, we've got 6 slope coefficients, we've got 2 error term variances. We've got 3 explanatory variable variances. We've got 1 covariance between the error terms. And we've got 3 covariances between explanatory variables. And so there are 15 parameters that need to be estimated in order to fit this structural equation model. Now, while we're at it, let's also calculate the model degrees of freedom. And so we have 5 manifest variables, V1 through V5. The number of parameters to be estimated, we've just calculated to be 15. And so the model degrees of freedom is given by P times P plus 1 all over 2 minus Q. That's 5 times 6, or 30 over 2, which is 15, minus 15. And so the number of model degrees of freedom is 0. And because of this, the model is said to be saturated. Step 5, let's construct a path diagram for this path model. Now, on the path diagram, we will also identify the error terms, the endogenous variables, as well as the exogenous variables. By identifying these variable types before fitting the model and comparing this list with the output from the software, this will help to verify that the model has been specified correctly using the SEM software. And so here we have the path diagram for the path model. V1 and V2 are the 2 response variables. The explanatory variables are V3, V4, and V5. The asterisks on the explanatory variables indicate variances that need to be estimated. In addition, the asterisk on the double-sided arrows connecting pairs of explanatory variables indicate covariances that need to be estimated. The error terms are E1 and E2. The asterisks on the error terms indicate variances that need to be estimated. And in addition, the asterisk on the double-sided arrow connecting the error terms indicates a covariance that needs to be estimated. Now, you'll recall that exogenous variables are variables that never participate in the model as a response variable. In terms of the diagram, endogenous variables are symbols that have no incoming one-way arrows. And so the exogenous variables are V3, V4, and V5, as well as the 2 error terms E1 and E2. On the other hand, endogenous variables are variables that participate in the model as response variables in at least one equation in the model. In terms of the diagram, endogenous variables are symbols that have at least one incoming one-way arrow coming into them. And so the endogenous variables for this model are V1 and V2. And finally, we have the slope coefficients, lambda 1, 3, lambda 2, 3, lambda 1, 4, lambda 2, 4, lambda 1, 5, and lambda 2, 5. Step 6, we fit the SEM in SAS PROC CALIS. And so here is the sample covariance matrix. Because covariance matrices are symmetric, only the lower triangular portion needs to be shown here and specified in the SAS data statement. The first step is to create a SAS dataset containing the covariance matrix of the manifest variables. And so here we have the data statement. The data statement creates a SAS dataset, which in this example, we're giving the name COVE. Now, when the dataset represents a covariance matrix, we've got to be sure that we specify type equal COVE in parentheses after the name of the dataset. In this context, the missing value dots represent values that are equal to their cross-diagonal counterparts, and therefore are not explicitly entered into the dataset. But we can't leave them out. If we do, that's going to cause errors. So we've got to be sure to include those missing value dots. Notice that in addition to the values in the covariance matrix, there is also a row giving the mean of each variable, in this case zeros since the variables have been centered, and the number of observed values for each variable represented in the dataset. The row containing the sample sizes is required, but the row containing the mean values is not. If the row for the means is left out, then PROC CALIS will assume that the means are equal to 0. Next, we're going to see how to specify the SEM in SAS PROC CALIS. PROC CALIS provides several different programming styles or languages for specifying structural equation models. In this lecture, we're going to be using the LINEQS modeling language. There are 3 main statements that we will be using to specify the model in PROC CALIS. The LINEQS statement to specify the algebraic equations in the model. The variance statement to define notation and specify values for variances in the model. The cov statement is used to define notation and specify values for covariances in the model. And then finally, we'll also use the path diagram statement to instruct SAS to construct a path diagram for the fitted model. So here we have the SAS code to specify this model to PROC CALIS. The PROC CALIS statement invokes PROC CALIS and indicates which dataset to use. The LINEQS statement is used to specify the regression type relationships in the model. And so we have V1 equal to L13 times V3 plus L14 times V4 plus L15 times V5 plus E1. We have a comma, and then we have the second equation comprising the system, V2 equal to L23 times V3 plus L24 times V4 plus L25 times V5 plus its error term, E2. The variance statement is used to define names for variances to be estimated and to specify the values of variances that are set by model assumptions and/or identifiability considerations. Now, in this particular model, we're not setting variances any particular value. We're just providing names for the variances that we need to estimate. And so here the variance of error term E1 is going to be called var underscore E1. The variance of E2 is going to be labeled var of E2. The variance of manifest variable V3 is var underscore V3. The variance of V4 is going to be denoted by var underscore V4. And finally, the variance of manifest variable V5 is going to be represented or denoted by var underscore V5. The cov statement is used to define names for covariances that need to be estimated and specify the values of covariances that are set by model assumptions and/or identifiability considerations. Now, covariances that are not given a name are by default set to 0. And so if there are covariances that are assumed to be 0, we don't have to really do anything with those because they will be set to 0 by default. And so in this statement, we are defining the covariance of E1 and E2 as theta underscore 1, 2. The covariance of V3 and V4 will be denoted by theta underscore 3, 4 in the output. The covariance of V3 and V5 will be labeled theta underscore 3, 5 in the output. And finally, the covariance of V4 and V5 will be denoted by theta underscore 4, 5 in the output. And finally, we include the path diagram statement. This is going to instruct PROC CALIS to produce a path diagram. And the XOG cov option instructs PROC CALIS to include double-sided arrows in the path diagram representing covariances between the exogenous variables. So let's look at the results of this initial model fitting. And so here we have a listing of the COVE dataset that contains the covariance matrix, as well as the values of the means and the sample sizes for the 5 manifest variables. And you'll recall that we don't have the raw data for this example, but we do have the covariance matrix as well as the sample size. And so this covariance matrix, along with the sample sizes, serves as the raw data for this analysis. Next, we look at the modeling information table. We see that we have 150 observations upon which the summarized data in the covariance matrix is based, and so that's been reported correctly to SAS PROC CALIS. We're using the LINEQS modeling language in PROC CALIS. The analysis is based on a covariance matrix as opposed to the raw data. Looking at the variables in the model table, we see that we have 2 endogenous manifest variables specified, V1 and V2, and so that's correct. We see that we have 5 exogenous variables, 3 of which are manifest variables and 2 are error terms. The exogenous manifest variables are V3, V4, and V5, and the exogenous error terms are E1 and E2. And so overall, we have 2 endogenous variables and 5 exogenous variables in the model. And that corresponds to what we came up with previously. Next, we look at the fit summary table. And again, we see that the analysis is based on 150 observations. We have 5 manifest variables in the model. The number of moments is equal to 15, and the number of moments is equal to the number of non-redundant entries in the covariance matrix, which we know is equal to P times P plus 1 all over 2. And so again, that is, in this case, would be 5 times 6 over 2, 30 over 2, or 15. The number of parameters is equal to 15, so that's been specified correctly. And then you'll recall that the model degrees of freedom is equal to the difference between the number of non-redundant entries in the covariance matrix and the number of parameters to be estimated. And so the model degrees of freedom is equal to the difference between these two values, the number of moments, which is 15, minus the number of parameters, which is 15. And so in this case, it's equal to 0. We next look at the absolute index portion of the fit summary table. And so we see here that we have 0 model degrees of freedom. And this corresponds to the calculation that we did previously. Note also that the chi-square value for this model is 0, and that's because this is a saturated model. We're going to use this value in our initial hypothesis test about the model. Next, we have the table for making inferences about the slope coefficients in the model. We have a column of point estimates for the slope coefficients. Next to that, we have the estimated standard errors of those point estimates. Next to that, we have the t-value corresponding to each of those parameter estimates, and the t-value is equal to the point estimate divided by the standard error. And then finally, in the last column, we have a column of p-values, and these p-values correspond to the test where the null hypothesis is that the slope coefficient is equal to 0 versus the alternative hypothesis that the slope coefficient is non-zero. Next, we have a table for making inferences about the variances. We have point estimates of the various variance components. We have the estimated standard errors of those point estimates of the variances. The t-value column is obtained by dividing the point estimate by the standard error. And then the p-value column contains p-values where in each row The null hypothesis is that that particular variance component is equal to 0 against the alternative hypothesis that the variance is actually greater than 0. Now notice that the reference distribution for these tests about variance components is a t-distribution. Now that may seem kind of strange because usually when we are testing hypotheses about variances, we're using something like the chi-squared distribution, which is a right-skewed distribution. And the reason we do that is because variance components can only take on positive values, and so they tend to have right-skewed distributions. In particular, when we're sampling from a normal distribution, the sample variance has a chi-square distribution. And so it may seem kind of strange that for these tests about the variance components, the reference distribution is a symmetric distribution like the t-distribution. We're going to talk a little more about this in a future lecture video. Next, we have a table that allows us to perform inferences about the covariances. And so we have point estimates of the various covariances in the model. We have their estimated standard errors. From the point estimate and the standard error, we can compute a t-value associated with each covariance parameter. And then finally, we have a column of p-values. And the p-values correspond to the test where the null hypothesis is that the covariance is equal to 0 against the alternative hypothesis that the covariance is not equal to 0. The reference distribution for these tests about covariances is a t-distribution as well. Now that may not be quite as surprising as it was for the tests about the variances, because covariances can take not only positive values but negative values. So this is perhaps not that surprising. Next, we have a table of squared multiple correlations. These are the coefficients of determination. And so the coefficient of determination, the r-squared value for response variable v1, is obtained by taking the total variation minus the variation in the error term, and then dividing that difference by the total variation. And so when we do that, we get 0.5680. And so what this means is that 56.8% of the variability in the response variable v1 is accounted for by the model. Similarly, 68.75% of the variability in the response variable v2 is accounted for by the model. And finally, we have a path diagram of the initial model. Now we can see here that sometimes SAS PROC CALIS has a little bit of a problem in terms of constructing a path diagram where everything can be read. And it is possible to go into a graphical editor in SAS and move these around. There are also some options on how different kind of methodologies to use in constructing the path diagram. But we're not going to get too focused on that right now. I just wanted to print out this path diagram to make sure that it has the proper structure. It has the one-way arrows from V3, V4, and V5 to both V1 and V2. It has two-way arrows between each pair of the explanatory variables, and it has a two-way arrow between V1 and V2, which actually represents the two-way arrow or the correlation arrow between the error terms on those two responses. And so based on this path diagram, it does indeed look like we have specified the model correctly. And so to summarize, the path model has been specified to PROC CALIS using the LINEQS programming language. The model has been fit, the parameters have been estimated, and all indications are that the model has been specified to PROC CALIS correctly. The next step will be to test hypotheses about the parameters in this path model. So that's what I wanted to show you in this lecture video. I'll see you in the next video.